For molecules that remain elusive to the human eye, a team of researchers at the University of Regina are using supercomputers to stimulate the cracking of bonds, carbon-carbon bonds. Professor Allan East and his team of researchers use computational chemistry to watch the chemical reactions during petroleum refining.
Petroleum cracking is a part of refining, oil refining. It's a very high temperature process. It involves a lot of energy in order to crack these carbon-carbon bonds. In things like the tar sands, we have these very long hydrocarbon molecules, and to make them into useful things like octane and propane, we have to crack the carbon-carbon bonds. There are catalysts to do this, but nobody really knows exactly how, at the molecular level, these catalysts actually crack the carbon-carbon bonds. One of the advantages of computational chemistry is that we can simulate and model these things. We have computers that are fast enough to crank through all of those equations of physics in order to make good predictions about energy and barrier heights, transition state structures, and so we can actually find out how these catalysts are actually cracking those carbon-carbon bonds. There's a new catalyst called ionic liquids that has been shown to be able to crack carbon-carbon bonds at much lower temperatures. If we can develop this new catalyst into a viable industrial process, that could save the industry a lot of money. The energy costs go down, so it's better for the environment because there's less energy use in order to do petroleum refining.
In order to affect major industry change, sometimes you have to go to the molecule of the matter. Chemistry master's student Abra Wagai says there is more to computational chemistry than meets the eye.
You can calculate everything possible. There is nothing that you cannot do using computations. You can do everything what is possible and what is not possible in an experiment. And you can explain the fundamental principles of chemistry in any chemical phenomenon.